Good morning, everybody. Thanks for coming to sixth of the COVID conference. As the chair of the first session, I would like you all, I welcome all to COVID fifth. And as you know, this is the CAD notation, so it starts from 0. So this is the sixth of the series of meetings which started in 2016. This conference is mainly about quantum optics, and as you know, while the quantum technologies are at the threshold of becoming part of our daily life, the fundamental research keeps opening new paths and new possibilities for new technologies. In this regard, COVID conference is bringing scientists from all around the world to share experiences, new ideas, and perhaps new collaborations. And while we are also in a pandemic, so I think I can think of the only benefit of COVID pandemic so far could be the widened use of these online tools and meetings. And this year, thanks to its online format, we enjoy geographically a wide spread of eminent speakers from all around the world. But this makes the scheduling of the talks challenging a little bit due to the local time differences. Well, in COVID conferences, in this conference, we have 2 plenary, 10 invited, and 8 contributed talks in the sessions. Today, there is an evening talk at 8:30 p.m. Istanbul time by Hakan Türeci. You can also join that one. And all of these will be live streamed in the YouTube over the COVID channel. Also, the pre-recorded talks posted as a playlist in YouTube, and poster presentations displayed in the COVID webpage. There will be an interactive question answer session on Friday, 23rd April, from 1 to 1:40 p.m. In the form of Zoom breakout rooms for those presenters that declared interest. Please use the same Zoom link to join this session. And for those speakers who give consent and do not withdraw this in the future, their live and pre-recorded presentations will be accessible even after the conference via the COVID YouTube channels. Today in the morning session, we will listen to invited and a plenary talk. I would like to move on to our first speaker of the session, Dr. Erhan Sağlamyürek. Dr. Sağlamyürek is a researcher working in the University of Alberta. He's doing research in the field of quantum information processing and quantum optics. Experimentally, he's doing research. I would like to thank him for accepting giving this talk, despite the inconvenience of the local time differences. I would like to pass the microphone to Dr. Sağlamyürek.
Thank you. Well, thank you very much for this introduction and for inviting me to this conference. Just I'm sharing my screen. Okay, so how's that looking?
It looks great.
All right, I'll just put this. This thing is popping up. Maybe I'll just close this. You know, people are entering the room. Okay, it's not. Okay. Thank you again for inviting me to this conference. So today I'm going to talk about our broadband light storage experiments using Bose-Einstein condensate. In my presentation, first I will briefly describe what quantum networks are, and then I will mention the role of quantum memories in such global networks. And following a brief review of the state of our quantum memories, I will introduce our technique that's relying on the Outler-Town splitting quantum memory. And then I will present our experimental results for the implementation of this ATS memory using Bose-Einstein condensate. And I will just conclude my talk with a brief discussion of our future works. So let's start with the big picture. As we know that quantum information science promises technologies that offers unprecedented computational power, unbreakable secret communication, and unbeatable precision. So while each of these technologies is progressing independently, one of the ultimate goals is to combine them under a single and global infrastructure, so-called quantum internet. So the concept of quantum internet is essentially similar to the internet that we use in our daily life. On the other hand, the way that it works quite different. So the realization of a future quantum internet relies on processing and storing quantum information at local nodes and interconnecting distant nodes using photons via fiber optic links or free space satellite-based links. So in this architecture then, while atoms or atom-like systems are processing and storage units, photons are the carrier of quantum information. So for the consideration of such a global network, probably one of the first questions that we have to address, how far we can send quantum information using photons. In this case, one may consider to use existing fiber communication links, relying on the amplifications of the signals at certain distances to overcome the transmission loss. As we know that unfortunately this strategy is not applicable in quantum information processing due to the well-known no-cloning theorem. So in this case, we may consider another scenario is the direct transmissions of photons from A to B, just using the standard fiber optic links, typically having 0.2 dB kilometer, 0.2 dB loss per kilometer. In this case, in this scenario, say that at point A, we have a single photon source generating photons at the rate of 10 gigahertz, and at point B, we have a single photon detector. And imagine that the distance is now 1 kilometer. So in this case, we will see that the generation rates and the detection rates will be almost equal, because this actually at this distance, the loss is really insignificant. On the other hand, if we extend the distance, let's say over 1,000 kilometers, the situation will be dramatically different. In this case, the detection rate will be lowered by 19 order of magnitude, meaning that to get to one click at point B, we have to wait approximately 300 years, which is obviously not practical. So to solve this issue that we are having here, one of the solutions actually is to use the architecture is called quantum repeaters. So this quantum repeaters relying on the dividing the communication channel into several segments or elementary links that I show only 2 of them for this example. So now in the operation of the quantum repeaters, in each elementary link, we have entangled photon sources, 2 entangled photon sources, PP here, and then also 2 quantum memories that allows storage and the retrieval of these photons on demand, as shown in this little animation. So in a standard operation, what we do is that we, in each elementary link, independently, we perform a Bell state measurements between the photons coming from the independent sources, as shown here. And this process swaps the entanglements, the other members of the entanglements, entangled sources. So that, at this point, using the quantum memories, we can actually store these photons. That means we can store this entanglement until all the other elementary links establish the same. So then upon this waiting process, imagine that my second elementary link also established the entanglement in the same way. And as a final stage, we perform a Bell state measurement between the elementary links just right here. And this allows us to establish the entanglement across the entire communication channel. So this way, that's relying on this architecture, relying on the entangled photon sources and the storage devices, is called quantum repeater, is one of the few solutions for long distance quantum communication. So now, in this case then, with this storage devices, our initial question of how far we can send quantum information translates into how long we can store quantum information. So to answer to this question, let's imagine again, we have this 1,000 kilometer link, and then we divide into 2 segments. And just by considering the speed of the light and the round trip of the photons in each elementary link, we can easily see that the minimum storage time that we will be requiring is on the order of 5 milliseconds, which is essentially a very long time for storing light. So unfortunately, we do not have any all-optical approach to store light this long time. So fortunately, we have atoms that are capable of storing light for a long time. So in atoms, we have 2 possibilities. One is that we can map photonic quantum information onto the excited or onto the electronic levels of the atoms that's shown here, G to E. And then the coherence time of this optical coherence can reach on the order of 5 milliseconds, as shown in this experiment. Even we can map photonic quantum information into the spin excitations of the atoms. In this case, the coherence time is even much longer. It can reach up to several hours. That means atoms are having capability to store light for a long time. On the other hand, to turn this atomic system a quantum memory that is useful for quantum repeaters, there are several other requirements that need to be fulfilled. So in addition to long storage time, these memory devices must operate with high efficiency, desirably above 90%. And also they should operate at high speeds, or they should have broadband operation for fast communication rates. At the same time, they should not introduce any noise that then in that way we can actually preserve the entanglement during storage. So simultaneously fulfilling all this requirement really requires engineering light matter interfaces. So this engineering actually has two aspects. The one is that we have to identify suitable atomic platforms. At the same time, we have to develop suitable light matter interaction protocols that allows efficient mapping of the quantum information between photons and atoms. So with this motivation, in the past 20 years, there have been several approaches relying on different atomic platforms and different interaction protocols. Among these atomic platforms, warm atoms, laser-cooled atoms, rare ion-doped solids, and single atom in cavities are the well-studied platforms. In addition to this, at the same time, we have several different interaction protocols like electromagnetic induced transparency, EIT, alpha-resonant Raman technique, and atomic frequency comb. So discussing all the features of these atomic platforms and protocols will be really beyond the scope of my topic, but we can easily say that each of the approach comes its pros and cons, and advantages and disadvantages. So we cannot easily say that up to now, there's no suitable combination where platform and protocol has been identified for high-performance quantum memory. At this point, we are proposing to combine the well-known Bose-Einstein condensate platform with our recently proposed outward time splitting light storage protocol. And the hope that by combining this platform and the protocol, we can have some unique features for high-performance quantum memory, as will be discussed in the next slide. So now, first thing, why Bose-Einstein condensate as a quantum memory platform? As we know that when we cool down the gas atoms down to the critical temperature that condensate occurs, one of the unique things is that the distance between the atoms become comparable, even smaller than the de Broglie wavelength, the matter wavelengths. So that means that in the Bose-Einstein condensate state, really the atomic density can be very large. So the density is essentially the unique parameter that determines the memory efficiency. In this sense, the BEC platform is inherently suitable for efficient operation. The other thing is that, as we know that when we go from thermal to the BEC regime, we are reaching to the ultra low temperatures that typically stated by like the nanokelvins. So that means that with this system, we already suppress the thermal motion, and in this way, we can have very long memory lifetimes. And these two properties really make the BEC platform very unique. With this motivation, essentially the PEC platform is one of the first atomic medium proposed for this the light storage experiments back almost like early 2000. The Linear House group at Harvard, they just demonstrate the ultra slow light effect using the BEC, and after a few years they demonstrate the storage of light in a coherent manner again using the BEC, and then later on they discovered the matter wave properties of the BEC for the manipulation of light, and finally back around 2010 they showed that they can store the light over 1 second in a BEC platform. So in the second generation of the experiments done by Erhan at Max Planck Institute, this actually, they sort of carried all this experiment to the quantum realm, and they show that it's possible to store polarization qubit with high fidelity using a BC platform. Even they demonstrated entanglement between a single atom and a BC. So if we compare briefly this, two generation of the experiments, we can see that the first generations is achieved like this in the classical realm. On the other hand, the second generation experiments did all this in the quantum domain. And the pulse duration, you see that as we from microseconds to a few hundred nanoseconds, efficiencies are typically 5%, 10%, and up to 30%, and storage time 1 second or on the order of milliseconds in these experiments. But what we can see that here, one common point is that the EIT protocol. So now the EIT protocol essentially is the very, very, very important tool in quantum optics. But as I will be describing now, it has some certain limitation for broadband or high-speed operation. So to understand this, let's look at a little bit less overview of this, the EIT protocol. So in this protocol, we start out with a 3-level Landau system that having the two spin levels in the ground state and the one excited level. This is typical an optical transition. So in this case, what we do is that we apply a strong control field from this unpopulated level to the excited level. What it does is that it actually induces a transparency window for this transition from G to E. And then this is called the electromagnetic induced transparency phenomenon. So what happens is that once we pick a probe pulse with a bandwidth sufficiently smaller than this transparency window, or in other words, it is sufficiently, the duration of this pulse is sufficiently longer than the optical coherence time between G and D, let's say that 100 times longer than the optical coherence time, then what we can do that actually we can see the slow light effect. The light is slowed down in the medium due to the steep dispersion feature associated with this absorption profile. So what happens is that in the slow light phenomenon, so while the pulse propagating inside the medium, there is a spin excitation associates, and then at the same speed, it moves at the same speed. This is the well-known polariton description of the slow light effect. The whole point is that in this entire process, we do not have any excitation between ground to excited level. It is an adiabatic process. So now this delay process can be turned into a quantum memory by actually switching off the control field while this pulse is propagated inside the medium. So then in this case, then we can trap the optical coherence in the spin wave form inside the medium. At a later time, we would like to get it back, and then we can switch the control field adiabatically back on, and then we can retrieve the signal. So this is an excellent protocol for long pulses, like 100 times longer than optical coherence time, for example. However, if we go down to the short pulse regime, let's say that 1/10 of the optical coherence time, the situation will be dramatically different. In this case, what happens first? So to match this broadband pulse, then we have to apply more control field. So then what happens is that instead of having narrow transparency window, now we will be splitting the absorption line, which is called another phenomenon called Outler-Town splitting. So now, once we have this one, of course, it comes with the expense of the large control field. For this example, this is almost 10,000 times more control power. This is number one. The second thing is that now, as you see, that this dispersion causing the delay is now not anymore that much steep. To compensate this one, compared to this case, we have to increase the optical depth approximately 6 times. So now optical OD 600 is quite high. So then actually, this is not only the demand of the control power and optical depth, this is actually the photonic noise processes in these systems scale with the OD optical depth and the control power. That means that having the low noise broadband operation would be very difficult with this EIT approach. So to overcome this, we propose a technique directly relying on the Outler-Town splitting. So what is this technique? So in this case, we take totally different approach of the EIT. Instead of eliminating the absorption, we mediate the absorption. How we do that? We actually apply less control field, like for this bandwidth, now we overlap this Outlier-Tom split line with our the probed bandwidth as shown here. So then in this case, actually, you see that there's no slow light effect based on dispersion. Rather, what we have that the photonic coherences exchange between the polarization and the spin in periodic manner in this way. So with this, actually, we do not have to have such optical depth anymore. Then we can reduce the optical depth 6 times. And then the control power also to have less splitting, nearly 15 times less. So now, similarly, like in the EIT protocol, we can turn this periodic delay process into a quantum memory. The way that we do, again, switch off the control field. But we do not have to do it in a adiabatic manner. It can be fast. And another property is that this control field during the writing and readout need to be 2 pi. It's a pulse area-based operation. In contrast with the EIT, it requires relatively tedious optimization, pulse shape optimization. This is another simplicity comes with this protocol. So then with this one, pulse area based operation, low optical depth, then significantly less control power actually brings also the low noise operation. As I mentioned, the noise, because the noise scales with this, the parameters. So in our initial experiments, basically what we did is that we explored experimentally these main features of the ATS protocol. And then we basically implemented standard magneto-optic trap, and this is a kind of the image of our cold atoms, like the 50 microkelvin and so. And then we use the rubidium gases, and this is our observation of the Outlier-Tom splitting. As you see, that is we increase the pulse, the control power. As you see, that splitting increases. So using this feature, we were able to demonstrate the storage of the short pulses on the order of 20 nanosecond. In these proof of principle experiments, we had the efficiency 12%. And then by changing the spacing between the write and readout, we can change the storage time as shown here, and efficiency drops due to the magnetic spin dephasing we are having in our system, which also limits the memory lifetime to microsecond regime. So, and also in this experiment, we have shown that indeed the phase of the light preserved during the storage, and we demonstrated with sort of the homodyne time measurements, and then this is the interference visibility that we observed. It is above 90% and shows that we can have actually high fidelity storage of the quantum information. Also, in another set of experiments that we have shown that our system can operate at the single photon level with quite a bit low noise. Here that we lower the mean photon number of the laser pulses down to 0.2, 0.1. As you see that signal to noise ratio still remains high, and this is another requirement for high fidelity storage. And also, we directly experimentally verify that it surpasses the performance of the EIT memory in this experiments for the storage of the 27 nanosecond pulses. As you see that the ATS memory gives 22%. On the other hand, the efficiency of the EIT is limited around 10%. So then after that, now, we wanted to combine these nice features of the ATS protocols, like the broadband operation and low noise operation, with these unique features of the BoseEinstein condensate platform. And obviously, it comes with some expense, with some additional complexity. So in this case, then, as I mentioned, we have to go down all the way this nano-Kelvin temperature regime. As you see that we have this, like, as you in the back that you see the dilution fridge, they are typically giving millikelvin. Now we should go down orders of magnitude low temperature. So the way that we do is after laser cooling, we perform evaporative cooling. So in evaporative cooling, in the final stage of the evaporative cooling, we transfer the atoms in an optical dipole trap to generate this BEC. And what we do is that we weaken the trap in a controlled manner, and it allows us actually to having transition from the thermal cloud to BEC. And then as you see that this is a velocity distribution, it's changed from the thermal distribution and the Thomas Fermi distribution as visible that as can be seen visibly is quite different in these two regimes. So, and after this verification, we have also another way to prove that we have BEC. we generate an anisotropic trap and release the atoms for a quantum gas that actually it should follow the Heisenberg uncertainty principle. That means that this aspect ratio should be changing to have this the conservation, the uncertainty relation. On the other hand, classical gas that keeps that the uniform, and then as you see that we see clear change in the aspect ratio of the cloud. This is another demonstration that indeed we have BEC our laboratory. So now with this BEC that we generate in the optical dipole trap, and as she is the shot that we have here, we have demonstrated the storage of the short pulses like 20 nanoseconds long. And then we were able to achieve the efficiencies 30%. In contrast with the laser cooled atoms, we got like 10%. And then as you see, the lifetime increased order of magnitude from 1 microsecond to 10 microseconds. So also we verified that indeed our BEC memory operates at the single photon level with low noise. So what we did is that here we generated pure BEC, and then like the temperatures around 300 nanokelvin, and then we store pulses with the mean photon number 0.2, and then this is the histogram that we obtained. And then we just did not send the probe field and look at the noise that's coming, that emerging from the system. And this black histogram showing that it's almost insignificant, not visible. So then it shows that actually our system is really operating at very low noise. And then we characterize this noise, signal to noise with respect to the mean photon number of the laser pulses. As you see that we can, at low mean photon numbers, we can easily have large signal to noise ratio. So in the next step then, we wanted to verify whether really we truly benefit from the BEC. So the way that we did is, while transitioning from the thermal to BEC cloud, as shown here, we looked at the memory efficiency. So before that, actually we analyzed the density of the atoms as we cool it down. And as you see that when we cool down, the density increased substantially. And on the other hand, the atom number decreases also significantly because of the evaporative cooling. So now let's look at the memory efficiency. For a probe pulse, the diameter is, let's say, that 65 micron, which is significantly smaller than the effective size of the BEC. As you see that memory efficiency decreases significantly. So what we do is that to overcome this, we did two things. One is that we reduce the probe diameter as much as possible down to 25 micron. And also we release the BEC from the trap in a way that we kind of have larger effective size, sort of we match the size. And this allows us to observe the efficiency indeed increases when we enter the BEC regime, and we benefit from large density. However, as you see that there is some drop, not very expected. The reason is that still the size of the BEC and the probe is really comparable, but this is purely technical issue. By reducing the probe size, we can indeed overcome this problem. And then another characterization, what about the lifetime as we cool down the atoms towards the BEC? And then there are three temperatures, 6.2 microkelvin down to 300 nanokelvin. As you see that once we lower the temperature, the lifetime of the memory increasing, and then from 5 micron, near the 5 microsecond to 15 microsecond. And this is due to the fact that, as I mentioned before, we are suppressing the thermal coherence. Unfortunately, still it is quite far from the milliseconds on second regime. In this experiments that we had, still this magnetic dephasing was quite effective in reducing the lifetime of our memory. And this is sort of the final, the slide that I just want to show that if we overcome this technical limitation, what will be the performance that sort of that this plots are showing? The first thing is that if we reduce the probe diameter down to 1 micrometer, as you see that the efficiency increased substantially up to 90%, even for the storage of the 2.6 nanosecond pulses. And the second thing again, once we enter the BEC regime, the bandwidth also, the optimal bandwidth increased substantially, and we have the fractions of the gigahertz, the expected bandwidth in our system. And the third thing is that the lifetime. So provided that we suppress this magnetic dephasing, actually what we expect is that our memory lifetime should increase up to 100 millisecond regime. And then at this point, we are limited by the inelastic collisions in BEC, and also there is some recoil motion effect, but nevertheless, it is almost reaching the fraction of seconds. It's quite long, potentially in our system. And finally, the noise. So we analyze the noise, four-way mixing noise strength for the EIT and HS protocol for storing really broadband pulses. And as you see that in the HS protocol, our expectation is 4 to 5 orders of magnitude less noise, again, due to the fact that the HS protocol requires much less optical depth and the control power. So our next goal is actually to really demonstrate a high performance quantum memory, and we would like to explore the capabilities, further capabilities for photonic quantum information processing. And actually we would like to reduce the size of this big setup. You have seen that in previous slides that, to really small size, even make it on chip and portable. And also the goal is really use this experiments like for satellite-based quantum communication. You probably already heard about that. There's already the BEC experiments going on in space, and especially Mustafa Gündoğan, my colleague, and Marcus Grützing in Berlin, they are actually focusing on this kind of the experiments. And that with that collaboration, one of the near future goal is to send this BEC experiment to space for global quantum networks. Thank you very much.
Thank you very much, Erhan Hocam, for the nice talk. For the audience, do we have any questions? So we can have the questions right now. By the time, if there are any questions, by the time the audience asks. So I have a question actually. In ATS protocol, you shown this fidelity graph. So in ATS protocol with the laser cooled rubidium atoms, what limits the fidelity, observed fidelity?
I see, yeah. So in this, okay, there is one actually, let me show, I quickly try to go there. There's two plots. So two things. One is that I don't know, yes, I think it's somewhere here. Two things I should say that the one is that the experimental imperfections, we had, 95% fidelity. The experimental imperfection in terms of the phase control of the laser in this case. And also the other aspect is that this was actually not really single photon level. It was pulses contain a lot of photons. We just look at only the preservation of the phase. It was limited by this mainly the laser related, the phase issues. So for this one, it's like signal to noise ratio. There's still some little bit noise even here, to not very visible. And it was like we figured out the scattered photons, like it, through glass cells, and it just, we get a little bit once in a while. That's why it's two things that limiting the fidelity, basically.
I see. Thank you very much, Hocam. Any more questions? Okay, if no further questions, thank you very much, Erhan Hocam, for the nice talk. We are getting closer to quantum internet, hopefully, with your efforts, and also looking forward to see the results of the BEC in space experiments.
Thank you very much.
Thank you, Hocam. Thank you very much.